So hopefully the sound will work on this one. We'll see. I'm not really sure. Anyway, we're talking about the natural logarithmic function and integration. So we're looking at the log rule for integration, and then also integrals of some trigonometric functions here. And then your homework is here at the bottom. Let me know, try that after you do these notes. Just try the homework and let me know if you have any questions on that. And we've already talked about this a little bit in the last section. I know you couldn't hear me, but that's okay. But we talked about this a little bit, where you integrate 1 over u times du. That's just the natural log. That's something you're going to have to remember. Okay, algebraically, you're not necessarily going to be able to work it out or whatever. So you just have to remember what that is. Another way to write this, the same thing, is that when you integrate, for example, u prime over u, that is just the natural log of u. So if you recognize that you're integrating a function where the derivative is in the numerator and the function is in the denominator, then that's just straight up natural log plus e. So let's take a look at some examples. So for example, you can rewrite this as 2 times the integral of 1 over x dx. So this is in that form up here because what's the derivative of x? Well, the derivative of x is 1. So this is in the form of u prime over u if u is x. So then that means that the integral of that is just 2 times the natural log of the absolute value of x plus c. And that would be your answer. So you notice on this next one, it doesn't necessarily follow that rule. You could make it look like, you'd have one thing that you could do is multiply it by 4 over 4. So 4 times 1/4 is just 1. If you get it to look like this, here's your u, you'd have 4x minus 1 in your denominator. Well, what's the derivative of 4x minus 1 is equal to 4? So then I know that my integral is just going to be 1/4 times the natural log of the 4x minus 1 plus c. And then that would be my answer. It's one way you could look at it. Another way you could look at this is just use U-substitution. So if we use U-substitution, u is the 4x minus 1, du is equal to 4 dx, and so then dx is equal to du over 4. So if we were to rewrite that integral, it would be the integral of 1 over u times, replace the dx with the du over 4, and then that, as you can see, is where the 1/4 comes from. And then the integral of 1 over u is just a natural log, so you'd have 1/4 times the natural log of 1 over u, and the u is 4x minus 1, so it's the natural log of 4x minus 1 plus c. Get the same thing. But again, in the blue, we just looked at it in terms of the shortcuts, fitting some general pattern and then going from there. So looking at this in terms of the area under the curve, here's your function. So if we want to find the area bounded, it's going to be the area, the integral of this function. So if it's ever bounded by the x-axis, it's just the integral of the function. Later on, we'll do what if it's bounded by other lines. But if it's just bounded by the x-axis, it's just the integral of the function. And it's from your point 0 to 3. And your function is x over x squared plus 1. Right? And then you notice you can't do anything about this, so we have to use U-substitution. So your u is going to be x squared plus 1, and then du is going to be 2x dx, and so then dx is du over 2x, like that. Then when we do these substitutions, still be from 0 to 3 of x over u times the du over 2x, and how nice, those x's will cancel, and everything's in terms of u now. that 2 can be brought out front. So it's from 0 to 3, 1/2 0 to 3, of 1 over u times du, and that should look familiar at this point. That's just going to be, come down here, 1/2 the natural log of u. And remember, u was your x squared plus 1, so you need the absolute value of x squared plus 1. Then you would have your plus c, but we're taking this from 0 to 3, so you're actually going to be plugging your limits in. When you plug your limits in, that 1/2 is your constant, so you'd plug a 3 in, so that would be the natural log of 3 squared. That's going to be 9 plus 1, so that's 10, minus the natural log of, when you plug 0 in, that's 1. So when you multiply this 1/2 in, so first of all, natural log of 1 is just 0. And then when you multiply this in, you'd have 1/2 natural log of 10. Then that 1/2 can go into the exponent, so you'd have the natural log of 10 to the 1/2, which is the same as the square root of 10. So all of that can be written as the square root, the natural log of the square root of 10. That's not a perfect square, so you can't simplify it any further. So here's just practicing that shortcut, being able to recognize these things, because you notice in the bottom, the derivative of x to the third plus 1 is 3x squared plus 1. So that fits that pattern that the derivative of u over u is just the natural log of u plus c. So that fits this one, that this is just going to be the natural log of the bottom u value, which is x to the third, plus x plus c. So if we look at these, again, try these on your own first, but if we look at these, it's just going to be the derivative of tangent is secant squared, so then that means this is just the natural log of your tangent function plus c. Same thing here. Okay, very similar thing here, except if you use U-Substitution, you notice this derivative is 3, so you're going to end up dividing by 3. Okay, you end up dividing by the derivative of this. So it's going to be 1/3 times the natural log of 3x plus 2 plus c. Alright, so you can look at these patterns and make things go a lot faster if you can recognize those patterns. Or you can just use U-Substitution, so your u in this case would be tan x, your u would be x to the third plus x, but you end up getting the same thing. So sometimes you'll come across a function where, like if you find the derivative of one of these, it doesn't cancel out with the other one. Okay, so the derivative of 2x plus 1 doesn't cancel out with that one, or vice versa. So you notice, in order for any of this to work, your denominator has to be of a higher degree than your numerator. Okay, in this case they're the same. So let's go ahead and quickly simplify this a little bit, or rewrite it by dividing. So you're going to divide the bottom into the top. And when we do that, remember, x squared goes into x squared one time. So if you multiply 1 times x squared, and then 1 times 1, and you end up subtracting them. So that gets rid of your x squareds, that gets rid of the 1, and you're just left over with x. And so this is going to be a remainder, because this is a larger value exponent, a higher degree. So that's your remainder. So you're left with plus your remainder over what you divided by. So that would be x squared plus 1. So this can be rewritten as the integral of the function 1 plus x over x squared plus 1 times dx. So you're able to rewrite that. And then remember, you can rewrite this as the integral of 1 dx plus the integral of x over x squared plus 1 dx. So you can break it up and integrate it separately. The integral of 1 is just x. Okay, and then you can use U-substitution here. If you use U-substitution here, just on this one at the right, your U is going to be x squared plus 1. Then du is going to be 2x dx, and divide out that 2x. So dx, so we're literally going to replace this dx with du over 2x. And then also we're going to replace the x squared plus 1 with the u, like that. And you can see that those x's cancel. And you're left with just the integral of, so it'd be 1/2, because this 2 can go out front. So it would be 1/2 the integral of 1 over u du. That should look familiar at this point. So it'd be x plus 1/2 the natural log of u, which is x squared. So the absolute value of that, plus c. And then that would be your final answer there. You could rewrite this, so looking at this, this is 1/2 times the natural log, so that 1/2 can go up here. So it'd be x squared plus 1 to the 1/2, or the square root of x squared plus 1, like that. So I guess that's the final way to write it. Okay, so this one's a little tricky, but this has to be U-substitution, and it's going to end up being a natural log, but let's use U-substitution first because we're going to have to do a lot with the variables. So u is going to be what's inside your composite function, that's the x plus 1 quantity squared. So u is just what's inside, so that's just x plus 1. Okay, and so then when you find the derivative du, that's just 1 times dx, so du is equal to dx. So right away, I can just replace du with dx, and then the x squared, or the x plus 1 with u, but I still have this x. And so if I rewrite this as u minus 1 is equal to x, now with this x, I can just replace that with, so I can bring this 2 out front, and then I'm going to replace the x with just the u minus 1. Now that helps me out because I can set that up as 2 different integrals. So that 2 I'll just bring way out front. And so my first integral is u over u squared. Then it's going to be minus the integral of 1 over u squared. Okay? And then let's try this. This u over u squared just simplifies to 1 over u, so you're integrating 1 over u, and that's just the natural log. So it's going to be the natural log of u minus, in this case you can't do natural log because this bottom is not to the first power. And so you would take the bottom, so that would be u to the negative 2. You would add 1 to your exponent and divide by that new exponent, so the u to the negative 1 over negative 1 is your integral. And so the net ends up being just negative 1 over u. Then when we multiply this 2 in, you'd have 2 times the natural log of u. And in this case, remember, let's go and plug u in. It was x plus 1. Minus, actually plus, because you have 2 negatives there. When you multiply this 2 in, it's just going to be 2 over u. And u was x plus 1. Then plus c. And then the only other thing that I see that we could do here is this 2 out front. Could bring it up and take the x plus 1 and square it. Not the whole natural log function, just the x plus 1. Okay, just be familiar with both ways to write it, because who knows what's going to be an option. But if it's free response, it doesn't matter the way that you write it at all. It does not matter. But multiple choice, yeah, you kind of have to be careful. Okay, so here I have a list. This is straight out of your book. Just guidelines for basic integration. Memorize the formulas. Just if you don't have those formulas, first of all, if you don't know the formula, then you're not going to be able to use it. Okay, and then look at the function and find the formula that's going to match the function that you're working on. Okay, so that's part 2. And then 3, if you cannot find a U-substitution that actually works, so substituting U or finding the derivative, plugging that back in, if that doesn't work, then try messing around with the integral, okay, or the integrand. Like for the one where we had x squared over x squared, you divided the bottom into the top, then you had something that you could work with. And then just be creative. Okay, mathematicians aren't known to be creative people, but for a lot of this, you have to be creative. You make stuff up, man. That's what we're doing. We're just making stuff up. And then if you have access to a calculator, computer software, whatever, use it. Okay, use it to your advantage. Whatever's on your calculator for the AP exam, the proctor is not allowed to look at your calculator, so you can have whatever you want in your calculator. So anyway, try this one, see how you do. This is going to take some creativity. Come back and check your answer. So on this one, you're going to set up u. In this case, has to be the natural log of x. So when you find the derivative natural log of x, remember, is 1 over x. So it's going to be 1 over x dx, and then dx is du times x. We're going to make that substitution. We're solving the differential, so we're integrating. Oh man. So then when you integrate, it's going to be 1 over x times u, because I substituted that in, times what's usually dx, okay? But instead of dx, it's going to be du times x. And then you can see that these x's simplify, and so you would just have the integral of 1 over u du, which is the natural log of u, and in this case u is the natural log of x. So it's a natural log of the natural log of x, and then since it's an indefinite integral, you have to include that plus c part. And then here you can write these down at your leisure if you need to pause the video, but just the integrals of 6 of the basic trigonometric functions, so that's sine, cosine, tangent, cotangent, secant, cosecant. So you can see again there's a pattern between sine and cosine, tangent, cotangent, secant, and cosecant. Okay, so if you can remember the one, you can probably remember the other one. So just know these as we go through this, and then also just add them to your list of things to have memorized for the AP exam. I know it's a lot, but remember, whatever in your calculator you're allowed to use on the AP exam, as long as it's a calculator allowed sections, calculator approved section. Alright, so on this one we're going to have to manipulate the function a little bit to make it look different. One of the trigonometric identities, if you look up on my wall, it's somewhere up there, is that when you have 1 plus tan squared x, that's equal to secant squared x. Okay, so we have to remember that. And so we can actually change this to, instead of the square root of 1 plus tan squared, we can take it and change it to secant squared. What that does for us, the square root and the square cancel, so you just have a straight up function that is the integral of secant x. And if you look just above in your notes, we know what that is. And so that is the natural log of the absolute value of secant x plus tangent x. And you're taking this from 0 to pi over 4. So we plug our upper limit in, minus our lower limit. So here's your upper limit. And then minus what you get when you plug in your lower limit. When we plug your upper limit in, be the natural log. Then it's going to be the secant of pi over 4 plus the tangent of pi over 4 minus your lower limit, which is the natural log of the secant of 0 plus the tangent of 0. Now if we look at these values, this is radical 2, this is 1, and this is 1, and this is 0. Looking at the unit circle for all this, because remember secant is just 1 over cosine. Cosine at 0 is 1. And then when we rewrite this, you'd have the natural log of the absolute value of whatever the square root of 2 plus 1 is, minus, in this case, the natural log of 1, which we know that the natural log of 1, well, I guess we don't know what the natural log. Yeah, we do. The natural log of 1, we went over that, right? 0. So then your answer is just the natural log of the square root of 2 plus 1. And that would be your final answer. And there's no plus c because there were definite limits that we plugged in to find these values. Okay, so here we have the electromotive force E of a particular electrical unit is given by that function. E is measured in volts, T is in time. So find the average value. So remember the average value is going to be 1 over b minus a times the integral from a to b of your function, times dx. And so then the average value, your b and a is 0.5 and 0, so it's going to be 1 over 0.5 minus 0 times the integral from 0 to 0.5. Your function then is 3 times the sine of 2t. So here you're going to have to use U-Substitution. So if I simplify this, 1 over 0.5, that's going to be 2. Then you can bring this 3 out. Using U-Substitution, your u is 2t. And so when you go through and solve for dt, it's going to be du over 2. So let's look at substituting that in. So you'd have then the sine of u times you'd have du over 2. And so I'm going to bring that 2 out, that divided by 2 out front. And so you would have 3 times the integral from 0 to 0.5 of just the sine of u du, which we know that's going to be the negative cosine. So it's going to be negative 3 cosine of u, and remember our u was 2t. Now we have limits of integration, and we're going to take that from 0 to 0.5. So we can keep that negative 3 out front. So you'd have negative 3 times the quantity of, when you plug 0.5 in here, that gives you 1. So it'll be cosine of 1 minus, when you plug 0 in there, you get 0. And then the last thing you could do is multiply this back in. So we don't know what I don't know what the cosine value of 1 is off the top of my head. You could plug that in the calculator, but oh well. So you'd have negative 3 times the cosine of 1, whatever that is, minus, so this is cosine of 0 is equal to 1, so that'd be minus a negative 3, but that'd be plus, because negative 3 times a negative is a positive, not 1, but 3. Because the cosine of 0 is 1, so that'd be 3 times 1. And then whatever this value is would be your final answer. And then we're going to answer that, in volts. So it might make more sense to find that. I don't have a calculator in front of me, so I'm not going to, but I'm just going to label this as volts. There we go. And so now that'll be our final answer there. Okay. So to review some of the things we learned in these notes here, we learned about the finding the integral, mostly of the integral of natural log, and lots of functions can look like that. Sometimes it requires you to use a natural log, sometimes U-Substitution. It just really depends. You have to really be careful. This is one of the trickier integration types of functions you're going to come across as the natural log. So just be really careful and lots of practice, and that's the only way that you're really going to get a sense of how to do these problems. So try the homework, come into class with questions, and then we can work on them from there.